In this video, we'll take a look at the first part of notes for section 23.1, which is continuity. So on the graphs at the right, which would you intuitively say is the graph of a continuous function? So as we take a look at the graphs on the right, notice that the first one has a hole in it. The second graph you can trace, but then it has a break to get down to the other piece of the graph. And then the third graph, notice you can trace it without picking up a pin. There are no holes and no breaks. So the third graph is a continuous function. So characteristics that make a function continuous is there are no holes and no breaks. So what does that mean mathematically? Or what is a better way to say that using mathematics? So if you take a look at our definition in the textbook in section 23.1, let me open our text. So when you access your textbook on MyMathLab, it says to help develop the concept of a limit, we first consider briefly the continuity of a function. For a function to be continuous at a point, the function must exist at the point. And any small change in x produces only a small change in f of x. In fact, the change in f of x can be made as small as we wish by restricting the change in x sufficiently. If the function itself is continuous, a function is continuous over an interval if it is continuous at each point in the interval. So let's take a look at and write down those definitions instead of no holes and no breaks. For a function to be continuous at a point, the function must be defined. That means for every x, f of x, there is a y coordinate. And then that takes care of the hole. And then the break, for a small change in x, there is a small change in f of x. And what that takes care of is the break. Okay, so if you notice at the holes, the function is not continuous at this point because it's not defined for that value of x. For this particular function, whatever this x value is, if we go to the right just a little bit, the y value, the function, skips down to the other break. So those are the two things that we look at for continuity. The function has to be defined, and for a small change in x, there's a small change in f of x. For a function to be continuous over an interval, it must be continuous at every point in the interval. So the types of functions that you've worked with so far that are continuous is you've looked at lines. The graph of a straight line is continuous. Parabola. Any of the polynomial functions, a cubic function, okay? Even exponential functions. Those look like exponential growth. So you've worked with a lot of functions that are continuous. Some of the functions that are not, and reasons why a function may not be continuous. It might have something like 1 over x. The graph of 1 over x is undefined at 0. And what the graph looks like, it looks like a hyperbola. It has two branches. Each branch itself is continuous, but it's discontinuous at x equals 0, where it's undefined. So when it looks this way, that's called a vertical asymptote. Or another reason why a function might not be continuous, it might have a hole in it or be undefined at a point. So when we take a look at graphs of functions, we state the intervals in which the function is continuous. So we can use the inequality notation. So on the first graph, think of these as having arrows on either end. For the first graph, this function is continuous everywhere, but it's only defined for x values greater than or equal to 1. So this is continuous on the interval x is greater than or equal to 1. So when we talk about intervals, we use x values. The second graph is defined everywhere or continuous everywhere, except, let's see, the function is defined at 1, but there's a break at 1. That means for a small change in x, there's a large change in y. So it's continuous everywhere except x equals 1. So we can write x does not equal 1. So this is continuous at all values except for 1. The next function is continuous everywhere except for where it's not defined, and that's at -2. So in this one, x cannot equal -2, but it can equal all other numbers. And our last example is a hyperbola, has two branches with a vertical asymptote at x equals 2. So this is continuous everywhere except at x cannot equal 2. All right, so what types of equations or what types of items give us graphs like this? Okay, so this second graph where you have, it looks like a part of two lines, that's called a piecewise function. So now we're going to take a look at functions defined differently, or piecewise functions. So a piecewise function is f of x equals, this particular function is two functions, x plus 2, a linear function for x is less than 1, and then -1/2 x plus 5 for x is greater than or equal to 1. So this function is defined as two lines, but on restricted domains. So to graph these, and we've got them graphed on the right, an easy way to graph is take a look at where they're defined, x is less than 1. So for this first equation, that x plus 2, I'm just going to plot a couple of points. I want to let x equal 1 because that's one of the values, that's where they're going to overlap. And that's where the domain is restricted. And then x is less than 1, so I'm going to pick another number less than 1, 0. If I substitute a 1 in the function, I get 1 plus 2, which is 3. Substitute a 0 plus 2 is 2. Then my function has an open circle at 1, 3. Another point on my function is 0, 2. Connect those two, and there's our straight line. The other function, -1/2 x plus 5, I'm going to do the same thing. Choose a value for x, have it be part of the restricted domain. We're going to put a 1. And then x is greater than or equal to 1, so pick a value bigger than 1, which is, say, 2. If we substitute 1 in the function, I get -1/2 times 1, which is -1/2 plus 5, which is 4.5. Substitute a 2, -1/2 times 2 is -1 plus 5, which is 4. So notice it's x is greater than or equal to 1, so I have a solid dot on the coordinate 1, 4.5. 2, 4 is another point, connect, and that's how I get my two pieces of the function. It's continuous everywhere except for where this break is, so it's continuous everywhere except x can't equal 1. All right, last example. Try graphing a piecewise function on your own, so you might want to pause the video, see if you can graph the function, and then come back to the video and see how you did. Okay? So we're going to graph two functions. I'm going to just use by plotting some points. Y equals 2x minus 1. The domain, or the restriction, is x is less than or equal to 2, and then x is greater than 2. So I'm going to make sure I use 2 as one of my coordinates. X is less than or equal to 2 for this first function, so pick a value smaller. I'll pick 0 just because it's easier. So I get 2 times x minus 1. 2 times 2 minus 1 is 3. Substitute a 0. 2 times 0 is 0 minus 1. So I'm going to graph my function over here on the right. At the point it's less than or equal to, at the point 2, 3, I have a solid dot because it's less than or equal to. Plot 0, -1, and then draw in the portion of the line less than or equal to 2. Now we're going to graph the other line for x is greater than 2. Select values. I'm going to select 2 again, and then x is greater than 2, pick another value, just any value greater than 2. Substitute a 2, I get -2 plus 5 is 3. Substitute 3, -3 plus 5 is 2. So the coordinate 2, 3 is there for greater than, so I have an open circle, and then 3, 2. So what happened with this one is that these two pieces of the graph ended up overlapping at the coordinate 2, 3. So even though it's not defined for this graph, it is defined for this graph. So it ends up, it fits for continuity. Every place is defined. There are no holes in the graph. And also, for every small change in x, there's a small change in y. So this is continuous for all values of x.